Welcome to Project Zippy Wheels. Our idea was to build electric roller skates by November 20th for $300. This is part of ECE 4960 Senior Design 2 at Clemson University. The team members are Melody Eckerd, Xander Hagler, Nitya Harry Kumar, Carly Kessler, and Covington Loftus.
Our objectives for this project are that there are many electric transportation devices, such as skateboards and scooters, that already exist. Our objective is to create electric roller skates that are smaller, more portable, and more convenient than other options that exist on the market. We wanted to create these because it would give our EEs and compies experience with different kinds of hardware and software while implementing these skates, and would also give us a breadth of new things to learn and experience over the course of this project.
Let's go over the primary goals of the project. The first major goal is to create skates that are accessible to a wide range of users. We wanted to design skates for users who weigh up to 185 pounds. We wanted to ensure that the skates could smoothly accelerate from 0 to 10 miles per hour. Our second goal was focused on safety. We wanted to incorporate safety features such as an emergency stop and a gradual speed up and slow down. Our third feature was focusing on endurance. We wanted to design the skates to be able to run at a consistent 5 miles per hour for at least 1 hour. This ensures the users can take longer rides without worrying about power loss or performance degradation. Our fourth deliverable was to design a housing that fits within a 4-inch by 10.5-inch by 3-inch footprint. Our fifth goal was to make sure that the skates, to incorporate wireless communication between the user's remote and the skates. This would enable seamless control of the skate speed and even the emergency stop function, all without the need for physical wires. And last but not least, we wanted to design and mill the PCB for the remote specifically, ensuring that it fits comfortably in the user's hand while maintaining all necessary features.
Our design consists of 2 skates and a remote control. The skate body is comprised of a 3D printed PLA housing that sits on top of 3 wheels. The front wheel is a brushless hub motor, while the 2 rear wheels are idle and provide support. Inside the housing, we have our battery, our electronic speed controller or ESC, and our receiver. On top of the housing is a lid that the user stands on and has Velcro straps to secure the user's feet. The outside of the skate body features a port for charging the battery and a fused disconnect switch for turning the power to the skate on and off. The remote control is also made of 3D printed PLA and contains 2 transmitters and a 9-volt battery and allows the user to control the speed of the motors from one hand.
So, for our system to function, we implemented a closed-loop feedback design. We have a remote that houses a Raspberry Pico in it. That is our human-machine interface, where we have a slider that generates a reference signal as we change this slider. That reference signal is then passed to a Pico that exists inside the skate itself. That Pico is told to generate a signal that biases a level shifter IC that then biases our electronic speed control unit that then tells the motor how fast to go. The level shifter IC is responsible for stepping the voltage of the PWM that the Pico inside of the skate generates. The ESC is able to control the speed of the motor, and then we are using a Hall effect sensor to actually measure the speed of the motor, and then that speed that we measure can be subtracted from a reference signal to generate an error signal, and this error signal can use adjustments in our system so that we have a closed loop feedback and our skate can adjust its speed to our reference signal.
For our hardware design, we had a goal to produce 120 watts for 1 hour of use or 5 miles. For the thermal budget, we wanted to have a max temperature of all the components of no more than 80 degrees Fahrenheit. We had a goal baud rate of 500 kilobits per second. We have a range of speed from 0 to 10 miles per hour on the skate. And we wanted our skates to be adjustable so that a lot of different people could use them. So we wanted to target US men's sizes 4.5 to 12.
So, in order to power our system, we decided to build our own battery pack. This battery pack is wired in a 6S 1P configuration that consists of 6 Samsung 18 650 cells that are wired in series, totaling a nominal voltage of about 22 volts for the system. Our battery pack is also able to output 2.5 amp hours, and we have a battery management system wired between each cell so that we can have active cell balancing for charging and discharging of the batteries.
The motor for the skate is a 3-phase 150-watt brushless hub motor rated for 24 to 36 volts. The motor is controlled by the ESC, which converts the battery's DC voltage into 3 alternating voltages in a sequence across each phase of the motor, allowing it to turn. The speed of the motor is determined by a PWM signal sent from a Raspberry Pi Pico receiver to an analog input pin on the ESC. The speed of the motor is based on the duty cycle of the PWM signal, which varies between 0 and 100%, allowing the motor to spin at speeds between 0 and 1200 RPM. Since the analog input pin on the ESC is rated for 5 volts and the amplitude on the PWM signal from the Pico is only 3.3 volts, we use a level shifter integrated circuit between the Pico and the ESC to step the voltage of the PWM up to get full range of speed for the motor. A 3-phase Hall effect sensor on the motor also connects to the ESC, which uses internal logic to output a square wave pulse signal whose frequency is proportional to the speed of the motor. The Pico takes this signal and uses it to calculate the output speed and perform closed-loop feedback for the system.
For the skate housing, we decided to go with a 3D printed material of PLA using 70% infill to provide stability. We also added holes in the front and back of the body for airflow so that we can keep to the target temperature. We also have a port in the side of the body for the charger and for the power switch. Inside the body, there's also 2 walls in there to hold the battery pack in place. And on the lid, we decided to go with a backing on the rounded edge to keep your heel in place, as well as 4 hooks on the top of it to put Velcro through to attach your foot into the skate. There's also a lip on the underside of the lid to slide onto the skate body and lock in place.
For the remote circuitry, we used 2 Raspberry Pi Picos powered by a 9-volt battery that was stepped down to 5 volts using a voltage regulator. There are 3 controls on the remote: a wheel potentiometer to control the speed of the skates, a push button that acts as a dead man switch to stop the skates from accelerating if not pressed, and an on-off switch to control the power. A custom PCB was designed in KiCad to fit all of the remote's components within a desired footprint. The dual-layer copper PCB was milled using a CNC machine, and each component was soldered onto it. The control components were connected using flexible wires to allow for proper positioning within a 3D printed housing.
Let's look at the software design requirements. The first requirement is that 90% of the packets would be received correctly through Bluetooth communication. The second requirement was real-time operation with less than 1 second delay. The third requirement was that the speed could be achieved with a 5% margin of error. The last requirement was that the speed would be able to reach 99% duty cycle. This is achieved through pulse width modulation, which allows us to control the amount of power delivered to the motor.
Each Raspberry Pi Pico on the remote transmits an integer value via classic Bluetooth to its paired Pico on the skates. This value is based on the voltage input from the potentiometer and is converted to an integer using an analog to digital converter. The value is only sent if the button is pressed, otherwise a value of 0 is sent. Since these numbers are used by the skate microcontroller to set the speed of the skate, the function of the button is an important safety feature.
Let's dive into the software design behind the skates. To achieve precise speed control, we used a closed-loop feedback system that relies on the Hall sensor data. This sensor tracks the motor's rotation and provides real-time speed feedback, helping the software adjust the motor power to match the user's desired speed, even as the load or conditions change. Now, to control the motor speed, we had to adjust the PWM, or pulse width modulation signal, which controls the power sent to the motor. The higher the duty cycle, the more power the motor gets. However, The Raspberry Pi Pico uses a 12-bit ADC, which is the value from the potentiometer, or what the user sends, but has a 16-bit PWM resolution. So we had to scale the 12-bit value in order to get finer control over the motor speed.
In order to actually build and construct this whole system, we utilized a top-down modular approach to design and build our skates. This way, different modules could be worked on independently and brought together at the end. Examples of these modules are the motor drive, our battery system, the remote circuit, our Bluetooth connection, and our skate housing / mechanical design. The idea with this system is that as we build and construct our system, we can change one of the modules out one at a time while keeping other things constant so that we can understand what is working and what is not working.
To calculate the required specifications for a motor, we started with determining how fast we wanted the skates to accelerate from rest to full speed. Using this acceleration, we took the target mass of the user and calculated the required force. Using this force, we used the radius of our skate's wheels to calculate the torque needed for the whole system, then divided it by 2 to get the torque needed from one motor. We then used our desired maximum speed and wheel radius to calculate the top angular velocity of the motor, which we converted to RPM to determine the minimum top rated speed for the motor.
We put the Zippy wheels through multiple different tests to ensure that they were working properly and as safe as we could make them. We tried a speed and acceleration test, a battery life test, a temperature test, as well as the stability tests.
We conducted several tests to measure the performance of our design. We did a speed test to determine if the Hall sensor feedback worked properly. We ran a single skate at 3 miles per hour and 7 miles per hour with and without a load. By measuring the time it took to cross a yard, we were able to calculate the actual speed of the skates and compare the runs. We determined that the Hall sensor was functioning correctly as the speeds were within 0.2 miles per hour at the lowest speed and 0.8 miles per hour at the highest speed. Due to the restriction in space of this test, we found that to be a reasonable difference. We also tested the battery life and temperature. We measured the voltage of the batteries and then ran our motor at its top speed of 10 miles per hour with no load for 15 minutes. After that time, we measured the voltage again and extrapolated an estimated voltage loss of 1.2 volts per hour. This minimal voltage loss will allow our skates to run much longer than our requirement of 1 hour. During this test, we also measured the temperature of the batteries every minute. Throughout the experiment, the temperature stayed within 72 and 74 degrees Fahrenheit, which is below our max temperature of 80 degrees. These tests confirmed that our skate met design requirements and functioned as expected.
As with all projects, ours was not without its challenges. We had some issues with the 3D modeling and printing as far as the size that we were targeting versus the size of the build plate that we were using, as well as the strength of the material and how much infill we had to use and how that caused a challenge for timing and for the printer itself. And then we had some challenges with the mechanical design once we had everything printed, just for the tolerances with how the lid fit together to the main skate body. There was also some limitations with the Bluetooth connections, with where the Picos could only communicate 1-to-1 for the sender and receiver. So we ended up using a total of 4 Picos in our design instead of the original 3. And then there was also some issues with the PCB design for the sizing of the traces on our CNC that we have in rigs, as well as the timing, again, if we wanted to make it smaller and get it sent out somewhere instead of doing it ourselves to fit better into our remote housing. And we just went with the alternative to do it in-house, but make it a little bigger.
The system is compact, more portable, and more convenient than electric skateboards and scooters. As you can see in this video, the skates take up much less space when compared to skateboards and scooters. The person on the skates is also able to gain good speed here, considering the fact that they are in a small enclosed space. In this video, we can see that the stability of the skates is not the greatest. The left skate likes to move to the left because the skate body was warped when it was 3D printed. Our stability issues stem from our front axle not being the most stable solution for our system. Overall, we of Team 4 are very happy with the overall performance of these skates.
To conclude, we were able to design and build an electric roller skate system for approximately $350 that can support 185 pounds, go up to 10 miles an hour, and run for at least an hour. We implemented safety features such as a dead man switch and a gradual speed up and slow down, and users are able to control the skates using a wireless remote. We achieved our goals for this project and advanced our skills.